So let's talk about acceleration. Velocity, you'll remember, was the time rate of change of displacement. Well, acceleration is the time rate of change of velocity. Now, we use a little a for acceleration, and notice the units. This often confuses people. Acceleration is the time rate of change in velocity. Velocity, like speed, is measured in meters per second. So acceleration then is meters per second. It's the number of meters per second that the speed changes per second, every second. So acceleration is meters per second, which we tend to write as meters, seconds to the minus 2. Now, just because it's interesting, we won't use it in this course, but there is another one after that. Velocity was the time rate of change of displacement. Acceleration is the time rate of change of velocity. And jerk is the time rate of change of acceleration. Now, we're not going to use that because most of the situations we do, apart from vertical circles, most of what we do is going to involve a constant acceleration for the linear motion. Constant acceleration. So we won't worry too much about the jerk. But when you start analysing, for example, show rides at Dreamworld or things like that, then you might want to start talking about the jerk. It's what you feel, jerks you around. Now, because we're talking about the change of velocity, we're going to use a simple convention because we're going to need initial velocity and final velocity. Now, I think I did mention this before. Initial velocity we're going to use as u, and final velocity we're going to write as v. Let me show you some examples. Kaitland merges onto a highway. She accelerates from 10 metres per second to 22 metres per second over 6 seconds. Calculate her acceleration. Well, the acceleration is the change in velocity over time. Now, I've written this with a delta. That's a capital delta, a triangle. That means the change in. If you've done some calculus already, you'll recognise that notation. The change in velocity is the final velocity minus the initial velocity, still over time. Now, I may not always write this, but this is what we have to do to work it out. The change in velocity, final minus initial, divided by the time it took. Now, in this case, and the next one as well, we're only going in a straight line. So the only thing we have to worry about for the direction of the vector, because remember it's a vector, because velocity was a vector, so acceleration's a vector. The only thing we have to worry about for direction is forwards or backwards. She accelerates from 10 to 22, so the final velocity is 22. The initial velocity was 10, and the time it took was 6. So we have 12 over 6, which is 2 metres per second. And what I said, this is meters per second velocity, and this is seconds. So we get meters per second. That's the acceleration. Its direction, it's positive, it's forwards, she's increasing her speed. Dylan's truck is travelling down a straight stretch of road at 20 metres per second. He brakes over 5 seconds to slow down to 12 metres per second. Calculate his acceleration. So again, acceleration is the change in velocity over time. That was a messy triangle. That's final velocity minus initial velocity over time. Well, his final velocity was smaller than his initial velocity over 5 seconds. 12 take 20 is -8 over 5, which if you like decimals is -1.6 meters per second per second. His acceleration is negative. Now that's what I expect because he's actually slowing down. He's decelerating, so his acceleration is negative. Final example. Emma's motorcycle is travelling north at 12 metres per second when she turns a corner and heads west without changing speed. If it took her 1.5 seconds to turn, what was her average acceleration? Now, be careful. She hasn't changed speed, but she has changed direction, which means her velocity has changed. Let's do this carefully. She's going north at 12, and then she goes west at 12. Now, these aren't velocities. This is U, and this is V, initial, final. But what I have to do is V minus U over time. How do I do a vector subtraction? Well, let me do it in a different colour, make it clear. What I have to do is start with the V and then subtract the U, minus U. And I'm looking for this direction. That is V minus, V minus U. Let me fix that. And again, V minus U. I'm looking for this vector. Look at that. I was going north, now going west. To make that happen, I had to apply a force in that direction to stop it going upwards and push it to the west. So the force and therefore the acceleration will be in a southwest direction. Let's go back to calculating it. So I need V minus U. That's this. Well, how long is that vector? Well, it's this squared plus this squared and then get the square root from Pythagoras. 12 squared plus 12 squared square root over 1.5 seconds. That's the square root of 288 over 1.5. I'm not going to try and do that in my head. Here's my calculator. The square root of 288 divided by 1.5, 11.3. 11.3 meters per second squared. But acceleration is a vector. I need to give the direction. Well, this is equal to that in length, which means this angle has to be 45 degrees. So the direction is southwest. If these lengths were not equal, then you would have to use tan to work out this angle. It's just that in this case they're the same length. So the acceleration that causes Emma's motorcycle to change from north to west at the same speed is 11.3 meters per second in a southwest direction. Don't be concerned if that's a little bit strange to you right now. You will get used to it. The idea of acceleration having a direction. And even though the speed hasn't changed, the velocity has. You will get used to that idea.